All right, so episode 19. Um, I hadn't really intended doing this episode, but because I found these on the shelf this evening, I said I'd do it and get it out there because I've got a few messages about it, and I just thought let's do it. And as well as that, I kind of want the DFE cylinder head, which is going to feature next. I kind of want that to be a round number. Not that it matters, but it'll be nice to have that episode 20. So, this episode will be covering the intake and exhaust valves of the Formula One engine. Now, these ones are from the Cosworth. Let's call them the V10 or the V8. They're similar makeup. So that's the V10, the TJ 3 liter, and the Cosworth CA V8 2.4 liter. Um, Now, again, this episode is just to debunk a few myths. Um, Not that I'm going to carry on that theme in further episodes, but it's just to show you what's going on inside the intake valve and the exhaust valve. And indeed, we have a blank here. So these are all titanium. These are actual valves. This one here is a blank, which has been machined to near net shape for the Cosworth engine. Now, I'm not going to go too much into detail on the types of alloys that they're made from, but hopefully it should bring you up to speed with just the valves in general, how they're made, um, what they're made from. And in the second part, hopefully, I don't intend this video to be as long as the others. The others I think are running at about 40 minutes. I hope to get this out in about 20 minutes, so it'll be a bit shorter than normal. And the hands are spectacular, as always. There's a lot of cutting and machining when you have to do what you see in a moment to intake valve and exhaust valves. But moving on from that, so as you know, this is the intake valve, this is the exhaust valve. They would go like that in a cylinder head. Um, Look back. I'm not going to recover old stuff. Look back if you have to on how they work. Obviously, the pneumatic assembly will be here and here controlling them. Um, they're not like your normal valves in a normal engine, like your car engine. They're probably actually the closest I've seen to Formula One stuff, which is kind of relevant in ways. Um, I rebuilt, as some of you might know, I'm into motorbikes, and I rebuilt my R1200 GS, which many of you will know and laugh. It's an old man's bike, but I rebuilt the engine lately to just a bit higher specifications. Now, I won't go into that too much in case my insurance company is listening, but let's just say it's rebuilt and it's the same as factory. But what I did notice is the valves and the combustion chamber in that engine are the closest I've seen to all the engines I've seen so far, back 25 years. Um, the BMW GS engine is the same, which would be the K25, is the same kind of layout or lightness, um, cross section of it's most similar to Formula One engines which I've seen so far. Now, in a normal car engine, the valve stems are quite big. Like, as reference, it's not the same, but like this would be Formula One, but a car valve stem would be this size. It's not that size, but in terms of reference, it's ginormous. But so these measure roughly. Let's just zero this. Um, so these are 6 mil, 5.97, and they'd be reamed to 6 millimeters, the guides, and that's kind of, they're both the same, obviously. The valve guides are the material silicon bronze. Again, I can't remember the trade name. It begins with a C. Someone will point out in the comments. They have done before. It's irrelevant, but Um, Intake valve, exhaust valve. Now the exhaust valve obviously is a bit chunkier here, just because of flow. Now the intake valve on the F1 engine, you've seen it before, has got a ridge here. Let's see, can I zoom in? The light is actually terrible here. I have to move the light, but you can see a little ridge there. So it's about 1 millimeter wide, and I'm going to call that 0.3 mil high, 0.2 mil high. So the function of that is to, when you have the air coming in here and it comes in here and around and into the chamber, the function of that little ridge there is just because it has to break. It separates the without getting too into airflow, which I'll cover sometime again. So when air comes in, it tends to stick to a surface. It tends to follow a surface like that, an aerodynamic profile, and stick to it. Now there's a small gap between the airflow and that surface. Let's just draw it. So if you had a wing like that, let's just say, so you have the air coming over here, comes across here, it will separate there a small bit and go off that way. Now this area here is called the boundary layer. So there isn't an awful lot happening there in terms of let's just call it turbulence or flow, Reynolds numbers, all that I won't get into because it's just too boring. But air tends to stick to a surface, tends to follow it as much as it can. Now this here is diving down here, so there'd be vortices here, there'd be a bit of low pressure here, and it would, where am I on the camera, it would probably rejoin the surface again out here, but there would be turbulence here, just because the air has velocity coming off this surface and it would want to join that surface. But this groove here, as I showed you, the little ridge, is just, if you picture the valve like this, coming down here, here, so that's a normal valve. So the air comes in here, down the port, in here, hits this, nice and smooth, and goes in there. When you add a groove onto the valve, so if we have the valve again here, again drawn very badly, like this, but if you add a groove here, which is this one here, the air comes in here and it causes turbulence on the boundary layer, which is, sorry, that should be radius there. The air comes in here, around that, normally it would flow off here nice and smooth and into the cylinder head. Now the bore would be here, so it would redirect in around there. But if you put a groove here, it causes a little vortex going in here, which at low lift and low engine speed means that the air is turbulent going in here, and it just mixes with the air better. Now that's a very brief summary on what that groove is for. Again, I could do a 8-hour long video on it in depth, but that's that should hopefully explain that groove. That's in the intake valve only, obviously. On the exhaust gas is going out here, so it doesn't really care. It's going off into the exhaust system. But getting back to the guys in the pub, so there's been a lot of talk and a lot of messages and emails, as I mentioned, about the construction of the valves and about sodium filled valves, hollow valves, friction welded, all that type of thing. These are one piece valves. So I've machined this down here and here, just on the collet area. So you can see there where I've machined it, and here on the face area. So it's machined halfway, just to dispel, because it's like it's, I think I've got about 55 messages saying that they're sodium cooled. They're not. They're one piece valve. They're solid. They're not hollow. So you can see that there. And again, they're titanium. Um, and the same with the exhaust valve, as you can see there. Now, what you could do if you want, if you were unsure that this was not all the one material, you could put on a like a nitric acid, or any of you TIG welders that are there, you could put on a pickling compound. So you could brush it on there and wipe it off after an hour, and the pickling compound would show you if there was any joins, or intersections, differential materials, any of that. Um, any of you that have done a welding test will know that once you do a weld in whatever position, underneath, overhead, horizontal, vertical, pipe welding, um, they will cut the weld, polish it, inspect it under a microscope, and then put on an acidic compound just to show the penetration and oxides, or whatever, slag, and all that sort of thing. But these are just one piece. Now I have all the chemicals here, but I didn't bother putting them on, because I know these are one piece. And again, on the tip area, it's just all one piece. Now the lash cap goes on here, so that's your hard area. Um, these are replaced every now and again. I'll check the mileage, I can't remember, but they're replaced. Multi-piece valves and sodium filled valves have their downfalls, obviously, because they're hollow, number one, which these aren't. So a sodium filled valve would have a hollow area down here, over here, and up here. This would be filled with sodium. The idea is it would be a two-piece valve. Now you could have it joined here, where the valve would be machined up that way with a big countersink here. You'd put in the sodium. You would then put in like a countersunk button here, and it would be friction welded or TIG welded in here, this button, to encapsulate the sodium in here. And as the valve is going up and down, the sodium would travel up and down here to take the heat from here and bring it up here into the valve guide, and take it off into the coolant. But with these, that's not the case. Now, again, going back, a hollow valve could also be friction welded here and here. You'd have a different material here, just on the fire face, on the seal face, and it would be friction welded onto a more conductive material here. And again, this would be hollow, but these aren't that way. They're one piece. Titanium, now going back the years, it was titanium aluminium, but I think that was banned in I don't know what year. Anyone that has been following this channel, I don't do years, drivers, cars, I have no idea. I'm just about the engineering. So that's how they were done. One piece. Again, the intake valve, one piece, and one piece at the top. The lash cap would go down here, and that would be your what will I call it? Tappet clearance. You'd take off this. You'd put the engine together, measure the combustion chamber pressure that the valve was sealing, and you'd grind your lash cap. You know how to do all that, but just setting the tappets basically like the old engines. So that's kind of the valves. Now they are wasted. You can see there, just for extra flow, from there all the way down out to here. These are made by Del West. Generally, I think in nearly all Formula 1 engines, the valves are made by Del West. If I had cleaned this properly, their engraving is on there. It's there somewhere. So Del West in the States, they make those from titanium, and I think that kind of covers that. Now, what I want to do in this, will I pause it? How will I keep going? I'll probably pause it. Just to talk about how the blanks are made for these. So obviously these have to be perfect blank when you start machining them or forging them. Now, this is, let's put the cap on this. So this here is titanium as well. It's from a Cosworth engine. Now, this is an exhaust valve blank. So once the machinist gets the blank back from the forgers, it's machined down to near net. It's checked. As you can see, it's near net. There's a bit left on the stem. There's something left on the diameter as well, here at the tulip area, and on the OD there's about the normal 1 mil left, so you can hopefully see that. So it's machined near net. It's taken again, it's checked just for inclusions and all that sort of thing, and if it passes all those, it goes on to final machining, which makes the valve itself. Now, just to give a brief rundown before I pause the video, on inclusions and on general bad things. So let's fold this over. Let's get rid of that. So we'll fold this over. Like that. Just, it's not the same thing, but just to talk about inclusions in a way that hopefully everyone will understand. If you're casting a part, now I know a lot of people that watch this channel, because I get messages daily, are people that are starting off casting or want to cast parts. Now, these are very different to what those guys are doing, but it's a simple way of explaining. Let's call it, what will I call it? Let's just say simply faults in your finished part. So inclusions, oxides, the effect the environment has on your part, and all that sort of thing. So if you're casting a part, now let's say just a simple part, so you've got a mold here. So this is the top of the mold, this is the bottom, and you want to cast, I don't know, let's just say a cup. So let's draw in a cup here, or a mug, and you've got your handle there. So that'll be the cross section of the cup. Now, this isn't how you cast a cup, but let's just go with it. So you've got your gate coming in here. So the gate will come in here. There'll be a basin there, and your fill sprue will be here, and you would have a riser. Let's just draw it off there in a non-real example. So your riser would come up there, up to here. That'll be your riser zone. Don't cast a part like this, especially out of mug. So you'd pour your metal in here. It would fill up the cavity, fantastic, and it would come up the riser, and that would provide head pressure to keep all the metal lovely. So where you will get inclusions in doing Anthem is if you ever watch casting videos on YouTube where they're pouring aluminium, either one I've seen actually last week, a very high profile company which I won't name, they were demonstrating their 3D printing of molds. Um, they had a factory set up, and the sprue setup was just terribly bad. Um, Anyone in the trade will recognize it straight away what I'm going to say now. Um, they poured in all their metal here out of the crucible, and it flowed straight in into the mold and filled it. But while it was flowing in, the down sprue was empty, and it just flowed in. So when this down sprue is empty or not choked enough here, it will suck in air, as you know, and inclusions like hydrogen is the worst thing you can have in here. Um, so sucked in all this gas along with the metal, and as you know, when you've got a, a situation like that, um, the aluminium will cool going in here, and the air will also mix with it, and you'll have a, let's just say, a cup wall like this. So flows in here, and you might have a portion where the aluminium solidified. So you have a skin on the aluminium, molten here, and a skin where the air came in here, solidified it momentarily, and flowed into the mold. So that's your, like, similar to how you'd, if you've had made soup on the cooker at home, you've seen the skin on top of the soup. Imagine pouring all that into a bowl, and as we all know, we hate that. You've got your skin there. So that all goes into the mold, and you've got all these inclusions where it can fracture. So if you ever see a video where they're pouring aluminium and this down sprue here is empty as they're pouring it, they have no idea what they're talking about. You need to see that sprue choked enough here so that the speed is reduced enough for the material going in here so that it doesn't suck in air here. It's all the time full, and they're just pouring it in here. You've got your melt meniscus here, and they're just pouring it into the top, and it's flowing in nicely, choked enough, and this is just filling perfectly. So why did I explain all that? That needed to be explained to get on to how they make the titanium for these. So what I'll do now is pause it and explain that in a moment. So chat in a sec. Okay, so taking all that into account, all the oxides which is present when you're pouring metal like that, aluminium, all the atmosphere can come in here. They need to obviously make the titanium blanks for the valves in a much different method rather than this, because you've got impurities, the atmosphere, dross, slag, whatever. You don't want that, because your valve will fracture here if there's an oxide break in the metal, like the skin on your soup. So they do it in a different method. So let's move on. Now I will be doing a test in a moment, which you'll have to, if you're wearing headphones, you have to put the sound way down, but I'll give you a warning. So with titanium, or with high purity alloys like this, they do it in a different way. So they take a billet which has been made first with vacuum melting. They take all the components, they put it into a furnace, they induction heat it, and they get the basic structure of the material together. So you've got all that in a blank, which would be like, have I one here? I've got a test sample here. So when it comes out of the vacuum melt furnace, it will be like this, just a blank like that. Again, they're not huge sizes, they're just a small billet, and they're put into a furnace then again, which is called vacuum arc remelting, which I'll try and describe now. Hopefully it'll make sense. So that piece here, which you saw there, is then taken. Obviously, when it comes out of the vacuum melt furnace, it's forged down, it's machined, it's cleaned. It's just a nice billet, but there is a danger. There could be impurities from the atmosphere in it, from the process, from the crucible, and all that. You don't want anything in this blank. It has to be totally pure, because if there's an impurity here, it's going to fracture. So it's then taken into the brown paper again is totally out of hand as normal. So it's then taken into a copper bath like this, or a crucible, or a chalice, like in the chalice in Indiana Jones. Do you remember that one? But it's then taken into a copper bath like that, and the ingot is stood up inside the bath like that. So that'll be the diameter there. So you can imagine sitting here like that, and this is all inside an inert atmosphere. So it will be argon. There'll be no hydrogen. Hydrogen is the worst thing ever you could have inside. Sorry, I'll just slide you back a small bit. You can see the angle grinder there, which will feature in a minute. But this is all inside this. So the titanium blank is sitting here. This is copper. It's made contact there. The end of this would be fitted so that it sits here. There would be small same property material put here, just to provide conduction into this copper crucible, chalice, whatever you want to call it, bath. And then there would be an electrode brought down here. Now, with the differences between these two, when this was originally made, it would be induction heated in a not so good atmosphere with AC power. So you all know that. I'm not going to cover that because it's too vast. But an AC furnace, it's just a coil around that. It's similar to how your phone charges, inductive charging. It induces a current in here, it heats the metal and it melts. But in this one here, it's far more pure. You guys that are TIG welders will know it's a very similar process. So you've got argon in here. This is a strong, whatever you call it, earthed, let's call it that, to the bath, and you've got an electrode that comes down there like that onto the top of the billet, and this is again DC, not AC, and it will strike an arc onto the top of the billet and melt it down. Now the important thing to know about this is, as the billet melts, there's a controller here, like your MIG welder, or like your arc welder, or not your arc but your TIG welder, which will continually measure the resistance between these two, and it will feed this down here as it melts onto the top of the molten pool. So this is it's similar to the really old guys that are watching this, like over 50, 65. Any of you that have been involved with cinema or stage lighting, you'll remember the carbon arc lamps, which were two carbon rods like that. So when you're lighting a stage, the stage would be like this. Your actor would be standing here like this, and they would need a spot, which you've all seen in films or on stage. They need a spotlight. Now in the early days, this was done on what was called a carbon arc light. So they had two carbon rods which were controlled with a timer here, They were given power in here and here. They'd strike the arc between the two electrodes. There'd be a reflector behind them, and it would emit the light out here. And as these arcs burnt back, or as the rods burnt back, these rods were on timers, and they'd fold in and keep the arc constant. Now, these had a feedback depending on the voltage between these, or resistance, or whatever. As I said before, I'm not an electronic engineer, I won't ever be, but it'll explain the principle enough. As this arc diminished, these would wind in and project the light out here onto the stage. So that's how it was done in the early days. Similar to this, the torch, or the tungsten electrode, would move down as this was melting to keep it all molten, keep in contact, keep the arc struck, and it would form a perfect pool of the virgin, or the billet alloy, without any impurities, because it's all inert. So that's how the metal was formed. This would then be poured out into a mold under vacuum, under controlled atmosphere, and you would end up with a billet like this, or a bit thinner here, or whatever shape you wanted to pour it into. That would be then forged in a forging die, which is, many of you know about forging. You've seen it if you have what'll I think of, like a crane hook, or a what, anything with drop forged, basically, like forged, a spanner, whatever. So that blank would then be taken, it'll be a bit more near net shape than that, into a forging die, and it will be forged into a valve shape, which will be that. So how forging differs from machining: if you had a, let's fold back the paper again. I should probably buy whiteboards, but the paper will do for the time being. So if you had a billet like this, and you were to machine, like the grain will be going this way in the billet. So if you were to machine a valve from it, it would be this shape, down here, up here, and up here. So if you imagine this as for any woodworkers or people that have worked with timber, if you imagine this as a piece of timber, you would have short grain here. Same with metal. So short grain is bad. So this could break off here on the valve. So the valves instead are forged. So you would take a similar billet, but it would be put into a forging die. Let's just go down here and draw it smaller, because we'll run out of room. The billet would put into a die, and the die would be this shape, very roughly, like that. And it would be hammered in the die, so that all these lines would end up flowing into this shape, like that. So again, if you imagine it as a piece of wood, you're squeezing the timber in there, you're squeezing it there, and the wood grain, or the grain in the metal, flows that way. So there's no break points there and there. So if you Google forging dies, you can see what this is. Again, as I said before, you could get into a huge episode about forging, about materials. I don't really want to. I just want to touch on it briefly, but that's kind of why, or how it's made, the near net shape, which you see here. So the grain will flow from all the way along the stem and out here. There'd be no short grain, let's call it short grain, down here. It'll all flow out there, just for strength. So hopefully that should cover Formula 1 valves and exhaust and intake. They're not hollow, they've got no sodium, and they're titanium, as you can see again. And on the tip, this tip again doesn't run off a camshaft. There's a lash cap or a shim cap over it, so it doesn't wear. Now, one other thing that I want to cover, and this is where the headphone warning comes in. Any of you that have bought Formula 1 parts off me on the Buy Me a Coffee link below, thanks a million. Some of you have mentioned that there's tiny little touch off areas on them, and I'll describe that as, yeah, an area like that. You see that grinding mark there? Just there, right there where the light is. So some parts in these videos I send off to a company, they're actually in Dublin, and they test the material, make up what it is. Now, thankfully, with experience, I know what a lot of the materials are. Aluminium can sometimes be a gamble. It can be 2 series, it can be 5, it can be 6. But with titanium, in a lot of the videos, I just call it titanium just because it's easier. I know by the weight now. Again, this is all titanium. This was a piece I showed you a minute ago. This was a test piece to set up a robotic welder I had to design in an Earth atmosphere. So you can see the welds there. This is one piece, this is another piece, this is a piece, and this is another piece. But the purpose of this was just to set up the welder. So you can see the welds there. Some welders would probably cringe looking at this, but it was the first test piece and it was fully automated. But you can see how hopefully the all of the past video ends up with this blank here, which, as I said, is titanium. Now, just to do a quick show, getting back to what I said a minute ago on how I test for titanium, and headphone users, beware, it's a very simple test. If you've got a part in your workshop or you're wondering what it is and you want to check if it's titanium, steel, stainless steel, whatever, there's a very simple test you can do with an angle grinder, or a grinding stone, or a Dremel, or anything like that. Anything that's high speed with a stone or an abrasive disc. So with normal steel, you've all sharpened tools, chisels. It's got a kind of a yellow spark. So just to demonstrate on a pliers, a cheap pliers, it's not a good one. I'm going to do this pretty quickly in succession, just so you'll see. But so I've got tool steel. So let's line them up. So tool steel, stainless steel, titanium. So the sparks from this are going to be fairly yellow. Sparks from this stainless, this is 316. They're going to be not as yellow, but fairly cold. And titanium, they're going to be absolutely white, and you're going to know straight away. You're going to say, Jesus, what was that? Not something I've seen before. And you'll probably stop once you touch the grinder or the grinding stone off it. So headphone users, warning now, turn down your volume. We're going to do this test. So let's start with this. Okay, so starting now, turn down your volume way down. So that's tool steel, very yellow spark. Stainless. Yellow again, not so many sparks. Titanium, wait for it. So really white sparks, and many of So hopefully that should show you how to tell simply without sending off to a lab. And now a lab will charge you about it's roughly about 300 quid, 300 euros to test the specimen. So you know, this can be a good test at times. If you're in doubt, it can be a good test. Again, if you want to check tool steel, again, warning headphone users, this is M50 tool steel, so this is a billet from a Formula 1 Cosworth water pump shaft. It's M50 steel. So let's go again. Again, turn down the volume. So very yellow. And once again, titanium. It's like fireworks. So hopefully that should be that. Again, it ended up as long as the other videos, but it is what it is. So the next one will be the DFV head. Very excited about that. Huge amount of work. Brown paper's running out. I've got a new roll today, you'll be delighted to know. So thanks to everyone that has bought coffees, that has bought parts. It means a lot. I mean, this, as I said before, this channel, it's not for money. I've got a day job, as you all know, but at the same time, I just wanted to break even because, you know, it's costly. Buying parts is costly, but at the same time, I don't really mind. Now, one last thing, which I wasn't going to do, but I may as well do because I just see vice grips here. If you're machining titanium, which you will know, those that are machinists, I remember years ago, about 12 years ago, I got my first job machining titanium. I thought, right, this is great, and I bought titanium, and it's absolutely a bear to machine on what I call older type machines. And now, if you've got modern VMCs, tooling, and all that, it's totally fine. But what I didn't know at the time was that titanium is highly flammable. So I had the part machined, perfect, everything was grand, and there was a load of swarf on the lathe. It was a lathe part, and I was just finishing up the part, and I can't exactly remember what happened, but I think either there was a spark off the, I may have hit the tool rest off the part or something. There was a small spark anyway, but the swarf from titanium is flammable, highly flammable, which many of you will know, but I didn't know at the time, but I got a fair surprise. But just finished the video and not really intended, but there was swarf there, so let's just show you how flammable it is. Now, anyone that has done chemistry in school or in a career will know that one of the tests for coolness is burning magnesium strip, and it's very bright when you burn it. Well, titanium is kind of the same, and once it catches fire, it can't be stopped. So let's show you that now with this in the vice grips. Catch it here, hopefully not burn all the brown paper. Let me get a torch, one moment. So map torch here, and hopefully it all goes well. Again, not rehearsed. Hopefully it doesn't fall on the brown paper. Let's put no, actually, let's just go for it. Right, watch your eyes. So you can see how bright it is. So if you can imagine, you know, a huge amount of that catching fire, it gives you a surprise. And I remember afterwards I couldn't see anything for about, I think, 30 minutes. But I got the job finished anyway, and everything was fine. But just that's a quick overview on titanium, Formula 1 valves, and yeah. So see you in the next one, episode 20, and the almighty DFV. Take care. Good luck.